Hello everyone. My name is Abdul Rahim and my research topic is addressing hardware faults in automotive OS. So I have selected this particular topic as there are a lot of applications of operating system in automotive industry. However, most of these papers focus on the software related issues, but none of the papers address the hardware faults that are associated with the automotive industry. So, I'd like to begin with the table of contents. So, the table of contents is as follows. I'm going to start with the introduction part and then proceed with the problem statement, the motivating example, the hypothesis, the related research, the empirical evidence, conclusions, and some of the future work. This is all in regards to the automotive industry and the application of operating system in the automotive industry. So before starting all this, I would like to explain my problem statement and my particular domain that I have selected, the name of the domain that I have selected. So I have chosen the problem in automotive sector that deals with the hardware related faults, as I have mentioned, and how these faults can be overcome. So the domain is automotive industry. So there are a lot of transient hardware breakdowns that have grown very common in recent car systems. As a result, in order to provide enough fault detection or masking properties that fulfill the basic standards, dependability measures must be added. So production costs on the other hand have continued to be a major factor in this field. This has led to hardware consolidation and as a result mixed criticality of systems. So I would like to start off with the introduction part. So there have been disruptive innovations in the automotive industry such as connectivity, autonomous and automated driving, mobility as a service, and drivetrain electrification. These necessitate high performance computing that is also extremely energy efficient and power conscious. The enormous number of smaller processors that manage traditional body, chassis, powertrain, and other vehicle electrical system, these all must coexist with this high performance computing. So depending on the model and market positioning, they could be anywhere from 30 to 100 ECUs. An ECU is an electronic control unit. These electronic or electrical units designs are becoming increasingly centralized, and these are aggregating and integrating high performance computers across different domains. As a result, heterogeneous many core processors are becoming the most high performing, energy efficient, and low power solution for handling the various workloads. So I would like to move on with a motivating example which I have here. So the motivative example is that hardware defined automobiles are quickly evolving into software defined transportation platforms. So the latest automobile advancements such as smart infotainment, self-driving capabilities, and electrification rely more on software quality, execution, and integration than on mechanical inventiveness. Automobile OEMs uh, and other industry stakeholders are trying to keep up with the rapid pace of development. The significant cost of integrating and upgrading the amenities that consumers are rapidly demanding, such as high-end onboard assistance and ADAS, Advanced Driver Assistance Systems. One example I would like to give is collision detection system, LiDAR, which is more common in these recent automobiles, and also another example is blind monitoring or blind spot detection, and of course one of the most common thing is reverse parking assistant, which is present in so many cars today. So many automotive businesses use code from other industries to build their software stacks, including operating systems and essential middleware. because writing original code is far more difficult. They may dramatically lower their development time frames and expenses. So next is hypothesis. So what my hypothesis is exactly is about uh, how I'm going to begin and how what exactly is going to do in this paper. So it's to illustrate the ideas and issues more fully. I have selected this concept of sphere of replication. So for those of you who don't know what is sphere of replication, I'd like to give some light on the same. Sphere of replication is basically it's in both you can view in terms of both hardware and software centric view, but over here I have done in the case of it's a fault detection scheme basically. So that's how it is. And in this fault detection scheme, this sphere of replication identifies the logical domain protected by the fault detection scheme. That is, if any fault that occurs within the sphere of replication and propagates to its boundary will be detected by the fault detection scheme corresponding to the sphere of replication. So there are now three questions that are related to sphere of replication. For which components will the redundant execution mechanism detect faults? Answer to this question is components outside the sphere of replication are not covered by redundant execution and may need to use alternative techniques such as parity, ECC, or for fault coverage. The second question rises, what outputs must be compared? Failure to compare critical values comprises fault coverage. However, needless comparisons increase overhead and complexity without improving coverage. So the third question arises, which inputs must be replicated? Failure to correctly replicate inputs can result in the redundant threads following divergent execution path. So now I'd like to a little bit explain the logic and how I'm going to proceed with this. So in other words, the system is within if the system is within SOR, so and as long as the redundancy is used either in terms of triple modality or encoded values, which allows for at least fault detection. Once a value has been decoded and the SORS boundary is reached, and then the redundancy is removed. So this is how it works. So our strategy here tries to extend the SOR from the core application layer. That is, it replicates and water across the whole kernel execution while maintaining mixed criticality system realizability. The system call can be thought of as a gateway to the kernel's SOR. So this is thought of as a gateway to the kernel's SOR. In other words, so once at this point, redundancy in terms of EAN is applied and kept throughout the entire kernel execution. So in fact, if any data is processed within the kernel, that is the input parameters as well as the internal kernel state, has to be encoded all the way through the kernel execution. Only when reaching the border of the SOR, for example when concrete values are to be set in hardware registers, a value is validated and decoded. Consequently, all operations within the kernel must be able to handle the EAN encoded values. This is very important. This may also lead to unusual data structure design optimized for EAN support, rather than runtime or memory efficiency. However, a fully static embedded system provides a significant amount of system knowledge. To take advantage of this information, we aim to integrate the analyzed system behavior into the EAN code, which allows us to detect deviations from the expected behavior. Now, I would like to talk about related research. So, the related research includes there are so many papers, as I've mentioned before, that deals with OS implementation in software related activities. So one of the papers deals with to improve a model driven system engineering framework by allowing to generate OS configurations from high level control system data, and other paper deals with safety verification that is a must in each stage of software development in an automotive system. However, there is no or less involvement that deals with hardware related issues, and this is how this paper is related in dealing with hardware related issues in automotive system that addresses hardware transient faults. Now the next up is the empirical evidence and how I have what actual work I have done. So in this, I have used my static domain knowledge. We'll use static domain knowledge derived from static system design to solve both the challenges. So, um, all tasks and resources are known ahead of time as shown in the figure. This is the original application app.oil, app.c, and activate task of x. This is the original application. And then after system analysis, it is this is the generated application which has dosec.c, d underscore app.c, activate task x encoder. The OSIC specification provides for the construction of a comprehensive set of attainable OS states. This potentially enormous state space can be reduced with the help of a static analysis tool by taking into action or account the analyzed kernel interaction and resource requirements of the concrete application. This redundant data can then be used to improve defect detection by adding another level of dependability. Now, as expected after the pre-runtime analysis, the system generation stage integrates the system knowledge into the code word, utilizing the validation of the task interaction. The signature allows us the legitimacy of the call according to the examined program to be checked by entering the SOR with system call arguments encoded. As a result, even system activity is considered in the specific EAN code beneath control flow and data integrity. The resulting kernel dosec.c has a continuous SOR with specialized entries and checkpoints that define speared boundaries, where the encoded results are checked. Now concluding, we expect to face several intriguing problems here. First, we must develop good algorithms and data structures for our operating system primitives that work efficiently on encoded values. We can start with a small subset of primitives and build up from there because the OSX specification specifies various conformance classes. The second difficulty will be to keep the SOR as large as feasible in order to reduce the number of activities that are not covered. Clearly, any software-based solution's SOR border is the basic hardware registers. Now, the future work looks as this. Our target system domain is static OSIC like mixed critical systems as previously stated. The basic functions OSIC specification is compact, precise, and a suitable place to start when creating a safety critical OS. The OSIC kernel must enable reliable coordination and voting of the multiple replica jobs in order to achieve core-write protected applications. A composable OS design concept akin to the CIO family is required for such customization. While CIAO focuses on memory and runtime efficiency, we put a priority on effective dependability and features. Thank you for listening to my presentation.